Okay, so chapter 2 in your environmental science textbook there, McGraw-Hill Ryerson. Knock up that fan for now, we don't need that. The chapter 2 is called Science, Society, and Solutions. And section 2.1 starts on page 28, 29. There are some stuff that we're going to cover here that is part of the first section. Sometimes there's like basic science knowledge that's kind of a bit of a refresher at the beginning of each chapter in your textbook, which I think is actually pretty handy that they have that there. But you can kind of study that, read through that on your own. Sometimes we'll cover that in the notes, sometimes we won't. So the first part of your notes there, you should have some blanks there. There are different approaches to thinking about the environment. Okay. So the first approach that we'll study here is called the development approach. As much nature as necessary should be converted for human use. So if we're focused on development, hang on here, come on, back to me. If we're focused on development, that the development approach, that is, we're looking for every opportunity to develop the space, whether it's occupied by trees or desert or whatever, to be converted to human use. So that's a development approach. And of course, companies that are building houses, companies that are building dams, companies that are expanding in different areas, and people want to build a house on this beautiful island and stuff like that. They want to develop it. They want to kind of make it useful. A lot of times they want to keep the nature aspect of it, but its primary purpose would be, let's develop this for our use. Human creativity and ingenuity will solve environmental challenges as they arise. So if there are problems that are caused by development, then we'll be able to figure out a way to solve that problem, okay? That's the development approach. The preservationist approach says this: large portions of nature should be preserved intact. Nature has value of heart from human, this should be apart. Value apart from human use and should be protected at all costs. So you can make this a blank if you want. Apart. Nature has value apart from human use and should be protected at all costs. Okay, so that is a preservationist approach. We are wanting to preserve nature as is without developing it. A conservationist approach promotes human well-being but considers a wider range of long-term management decisions that preserve the environment. So it's a bit of a mix, the conservationist approach. Promotes human well-being, okay, and development and being able to live comfortably, but considers also a wider range of long-term management of nature. So those are the three main approaches. I'm not sure right now, you can think about this, don't answer out loud, but I'm not sure which approach you would largely fall under. Are you, would be in the development camp? Say, hey, yeah, I appreciate nature. I love the coast, the ocean coast. I want to go and live there. I want to build. I'd love to buy a piece. I'd love to make it something I can live and use. Are you a preservationist? No. We need to keep to ourselves as much as possible and let nature take its course. Or are you kind of a mix, a little bit of both? The conservationist, sort of that idea, I think largely it's closer to the preservationist than the developmentalist, right? But it's got a mix of both. So it's good for us to think about where our passions lie here and where we would fall. So many different areas of study contribute to solutions for environmental challenges. Political science, okay? And you see a graphic on page 30 there, okay? So for example, the goal in this graphic is at the center of the wheel. And it says the goal is a sustainable energy future. So what different disciplines or areas are involved? Political science. So which government policies lead to sustainable solutions? The making of laws, the application of laws, taxes, tariffs, all sorts of things, the politics of it. What government policies lead to sustainable solutions? Sociology. So sociology is how do people adopt new ideas? Society is the root for socio, so that is sort of people and how we live. How do we adopt new ideas? How can you convince people to do the right thing? Urban planning. What urban designs can reduce energy use? So how do you design towns and cities and infrastructure to reduce energy use or to be more efficient. Engineering is another one. Can we design better vehicles? Can we design better vehicles? So, or can better vehicles be designed to be more efficient and more environmentally friendly? Economics, what are the costs and benefits of different energy sources? So if you think of large-scale economics, these are corporations that study how money flows throughout the whole of the globe or throughout the country. There are economists that study and research the best way to be prosperous as a nation or as a company. So yeah, what are the costs and benefits? Ecology, how does energy production affect population? How does energy production affect population? So ecology is sort of our local environment and how things interact with each other. Chemistry, how can we make better batteries, for example? How can we use our knowledge of interactions of chemicals to be more efficient and environmentally friendly? So there, you can see there's lots of different disciplines that combine to solving environmental solutions. So if you have a passion for the environment and want to solve problems and create a sustainable future, there's lots of options for you. You can be a political scientist, you can be a politician, you can be an engineer, you can be a biologist or a chemist. Any of that, you can put your knowledge to solving problems as we move in through the future here. So I would draw your attention now to page 30. That's the wheel, the sort of the graphic that I mentioned. Also the key fields of study in the bottom part, there's a chart there. So biology, chemistry, earth sciences, physics, mathematical and related sciences, and social sciences. So sub-disciplines of these, that would be a part of environmental science. I'll just refer you to that chart. So if you were interested in chemistry, you could be a biochemist, a geochemist, or a nuclear chemist. Those are all contributing to environmental science. If you were interested in the social sciences, not the hard sciences, but the softer social sciences, you could study anthropology, the study of human civilizations. You could study political science or sociology, or even law, right? What sort of laws are effective to solving environmental science problems. So there's lots of different fields that you could go into and still contribute to the environment. All right, let's talk about 4 main methods of data collection. So we went to West Canada the other day and collected some water samples in our class here. So air, water, and soil samples. We collected some water samples. We can examine these samples over time, measuring how their quality changes. We could do multiple sampling to see if there are changes in the chemistry or in the biology. Number 2 is ice core samples. So ice fields in Antarctica have, I'm sorry, the typos here, I'll fix these. This is my first time through this, and I did dictate a lot of this, so I missed some of these. have existed. This should be existed. So it's just some more, some more notes to fill in here. Ice core samples have existed for many thousands of years in Antarctica. Studying the layers in the ice samples helps us to understand past global events. And of course, PAST, global events, past global events. So you see some pictures there in your textbook too. These ice core samples can be meters long, right? So, I mean, if you think about the ice sheets that have how they've changed over the years, you can actually see what was on the surface, frozen, fairly intact over time, like hundreds of years ago, thousands of years ago, I don't know. But anyways, they can kind of study what the atmosphere was like, what the gases above the ice were like, all that sort of stuff. Interesting. So quadrat sampling, that's one way of measuring biodiversity using a quadrat marker. And a quadrat marker is like a big square, like a big frame, and they might have like further divisions of the frame, and you plop it basically on the ground or the grass, and you get right down there with your hands and you count the different bugs or ants or whatever that are in that little area, and you do a sampling that way. So a scientist can count the number of different species in a known area to measure the biodiversity. Yeah, so especially if they're going from year to year to year, right? If you have the exact same area that you're studying and the exact same spot, or pretty close to the same spot, you know you're not going to overcount or undercount because the area will remain the same. So actually happens a lot. And statistical data. So data that you can find on the internet or that you can research in a book, such as birth or death rates. They basically tell us how human population is growing. For example, medical records can also indicate effects of air and water quality on human health. So there's a load of statistical data that can be researched and compared. Okay, so again, taking air and water samples, ice core samples, quadrat sampling for biodiversity, and statistical data from research online. An environmental impact assessment, this is an EI, an environmental impact assessment, is done before any large-scale environmental project to assess the possible effects on the environment. Large-scale environmental projects may affect aquatic species, so that is species living in water, so lakes and streams and ponds and rivers, and their habitats, so that is the the places that they live, movement of migratory birds, Aboriginal peoples, and sacred burial grounds and things like that. So I actually worked for a number of years in Alberta in the oil industry there, and I was a landman who. So my job was to work on behalf of the oil companies to secure legal documents, right-of-ways, pipeline right-of-ways, well site agreements, to negotiate that with the landowners and to make sure that all the legal stuff was taken care of so that the construction crew could go in there and start their drilling or start their pipelining. And long before I got my files to go in there and talk to the farmers, talk to the owners, and get this paper signed, they had to do a big environmental impact assessment. So this happened, it happens years before any shovels go in the ground or anything's dug up. They took a look at the area as a whole. They examined what, any kind of development, how that would affect the immediate environment and the kind of large scale effects. And so sometimes projects, like if you're drilling an oil well, sometimes those big large projects get held up or they get canceled altogether because of the larger scale environmental impact that is deemed unacceptable by the government or by related parties. So yeah, there's lots of stuff that goes into these big projects. So they try and make sure the environment isn't hindered too much. There's a certain tolerability, right, of how much disturbance on the environment is acceptable. All right, section 2.2. So that's section 2.1. And again, I would encourage you to read through the textbook as much as possible. You will see the highlights in these notes. You'll see those in the textbook. But there's more examples, there's pictures, there's even different websites, different reflection questions that you will see in the textbook that we won't always get to in class, but that would be helpful. There's also, like on page 33, there's a summary section. For each section, there's a summary section. So you should read through those, and most of that stuff all of that stuff really should be covered in the notes that we see. Question?
Yeah, on the book, the environmental impact assessment is short as EIA.
Oh yeah, they do have an A in there, impact, environmental impact. Yeah, so EI or EIA, environmental impact assessment, yeah. Yes, that's right, you're right, I'll add that too, so that's a EIA, and we'll say or. Yep, so environmental impact, EI or EIA, you might see it as well, so yeah, good catch. Okay, so the mindset of environmental scientists. Okay, this applies to a lot of fields of science, these kind of mindsets, but it's a way of thinking, it's sort of attitudes that one should have to properly and accurately do environmental science. So skepticism, a lot of times skepticism is seen as a very negative thing, but skepticism is just not blindly believing everything you hear or you read or you see. Open-mindedness. Okay, so open-mindedness is being willing to consider different points of view. And so if you have a strong feeling about something or think that you know about something and someone else has a different idea, you might go, oh, that's not right, But being open-minded is at least willing to consider what other people have to say, have to think, and the reasons why. So being open-minded is a positive thing in science. You might learn something, okay? You might even change your position because of the different things that you learn. So this is a good thing. Persistence, okay? Being willing to stick with the task or the study or the research long enough to accomplish your goals. So being persistent is another mindset of scientists, especially when you're taking samples and when you're involved in a large, long-term study. Persistence is a really important thing. And humility and honesty. Be aware that conclusions might not be supported by new evidence or information and being willing to change your mind. So be aware that the conclusions that you make might not be supported when new evidence shows up. And being willing to change your mind. So humility, being open to being corrected, and honesty, follow the evidence where it leads. Try and suppress your biases in the science if you can. Critical thinking skills. Again, I'm going over this pretty quickly because you've heard of this before, but this is, I think, really important in setting us up for how we approach science here. So critical thinking involves skills associated with thinking independently, systematically, and analytically. So learning how to actually analyze something. Okay, that's you kind of take things at face value a lot of times. We all do. We just kind of look and the first thing that we think of, that's our assessment. Well, you want to be able to think critically. So you want to think, first of all, independently. You want to think objectively. You want to think in a regular, systematic way, so that you are free from your biases or from missing something. And then analytically is, let's just really analyze why this is the way it is. Why am I seeing this? Why am I not seeing something else? So being analytical. So analytical thinking asks, how can I break this problem down into smaller, more manageable parts? So again, digging deep, breaking down into smaller, more manageable parts. Creative thinking asks, how can I approach this problem in ways that are outside the box? So thinking creative ways. Logical thinking asks, how can reasoning help beeping? Yeah, I don't think beeping is the word there. This is an interesting ride here today. How logical thinking asks, how
Period 5 biology class.
how can reasoning help?
If you're in Mr. Webb's Period 5 biology class, please bring your textbook.
I think beeping. I don't know. How can logical reasoning? Okay, let's look at our textbooks. I got this from the textbook. This is not copied out correctly. Logical thinking asks, how can reasoning help? I think I just maybe us see clearly, maybe. So let's find it. Okay, logical thinking asks, how can reasoning help me think more clearly? And finally, reflective thinking asks, how can I use my experiences and learning to help me make judgments about what has happened and what should happen? So reflective thinking is looking back and thinking reflectively. All right, study table 2.3 on page 35 before next class. Read through that. And read through chapter 1 and up to chapter 2 where we've been so far. Remember to beep clearly, that's right. Beep clearly. Beep, beep.